Recording. Okay, today we're going to switch gears a little bit and start talking about how we actually analyze the data. And we're going to really focus first on more, before we get into all the pre-processing and sort of how you sort of wrangle, we're going to talk more about sort of the higher level concepts in terms of, what are we actually trying to do and what are some of the statistical concepts behind what we're trying to do. And hopefully for most of this lecture, a lot of this will be review for most of you because you've already had statistics, right? Okay, and if not, then it'll be quite fast. Okay, so feel free to ask questions, but here we go. So, so this is a conjecture that's really only three things that you need for an FMRI experiment. So obviously you need a scanner, you need a brain, and then you need lots of software. Okay, and so a lot of the work over the last 25 years, 25 plus years, has been development of software for FMRI. And at this point in the history of functional neuroimaging, the software is actually quite sophisticated. I mean, there's probably millions of lines of code that have been written, and it's still being developed. Okay, so it's a never-changing field. So there's no way we can cover everything in one course, but we want to just give you some of the basic principles that you can use to guide your decision making. Part of that is sort of inspired by these quotes here. So Hubert Blaylock, who I'm not really sure who he is, but he wrote this book, and he said, the manipulation of statistical formulas, and in parentheses I put software, is no substitute for knowing what one is doing. So one of the advantages of doing fMRI these days is lots of software available. One of the disadvantages is you probably have no idea what it's doing. Okay, so in the early days, people wrote a lot of their own software, so they knew what was being done. Now you have your choice of software. It's very easy to make a mistake, and if you don't know what you're doing, and if your PI doesn't catch it, you could end up making a mistake that the reviewers might then totally trash you, or else it gets published and then someone else points out an error a year or two later. Okay, so it is instrumental. Okay, let's see, why is that happening? Let me just see if I can make it sure that the setting is such that it's not going to time out on me again. System preferences, screensaver should be off, right? Oh, I know, it's because I'm not plugged in. Okay. We didn't have as much time today to set up, so I forgot to do that. Okay, moving right along. And then the famous Bob Cox, who is the author of AFNI and has written many, many lines of software. His basic thing is you should understand what the analysis software is doing. Now, he can say that because he wrote most of the software. For most of us, that's going to be impossible. There's no way you're going to be able to know what every piece of software is actually doing, but you need to know enough to sort of make reasonable decisions. Okay, and then and you also have to know enough to know when you don't know what you're doing, and then you need to go seek out an expert. All right, so part of this course is trying to give you enough so you sort of know what you should know, and you know what you know and what you know what you don't know, and you know when you might be getting into trouble, right? Because the software will do anything you want it to do. Okay. Okay, so a lot of key concepts for today, but we'll try to sort of go through them at a pace where, and really what we're trying to do is just touch upon things that you're going to hear about, and when you're doing your analyses and using these software programs, there's going to be nomenclature, and today trying to just start orienting you towards what some of those concepts are and why they're doing what they're doing. Okay, so last time we talked a little bit about how the fMRI signal comes about. And the basic idea is I might have some stimulus that follows a pattern, say, shown by this red line. So that's what's called a boxcar design. It's just going up or down, also called a block design. So that's a very, very common design in fMRI. In general, when we ever want to test out something new, we generally just stick each other in the scanner and tap our fingers for 40 seconds on, 40 seconds off. And that's one of the easiest fMRI designs you could ever do. Okay? So when we don't want to go through the trouble of setting up all the stimulus and stuff, we want to just do a quick and dirty test of something, we'll do a boxcar design. And then what we get in the different voxels, if it's a voxel where there's activation, then hopefully you should see some activation. Okay? And if you don't, then you're like, oh, this new method doesn't really work, or something's wrong. So that's sort of a good test. One term we will be using a lot that you will hear is this term here, called the hemodynamic response function, often abbreviated HRF, although some people call it HDR, hemodynamic response. Okay, so you'll see both, but HRF is, I believe, what the Poldrack book uses. So after many thousands of FMRI experiments have been done, it is generally agreed upon that many HRFs look like this. Okay, this is sort of the canonical HRF. They don't all look like this, but they all tend to go up and go down. They tend to sometimes have an initial dip and a post-stimulus undershoot, but this is really just sort of saying that they generally have this form. You will see sometimes there's no post-stimulus undershoot, sometimes there's an initial dip, sometimes it just looks very different. But in general, over many sort of studies, it's generally agreed upon, and the field has generally come to adopt certain standard hemodynamic response functions. Okay, we'll talk a little bit more about that later in the slide, in the lecture. Okay, so the first thing we want to cover is we want to cover what is the basic model that all FMRI, or basically most FMRI uses. And what we're working up towards is something called the general linear model, or GLM for short. And so we'll talk at length about the GLM, but before we get into the GLM, I want to provide some basic motivation for why we think we can use the GLM. So today we're going to be talking about single subject analysis. Okay, it's basically you put the person in the scanner, you do some scans on them, and how do you analyze each of those scans? Okay, in later weeks, Alan Simmons and others will be talking about like group analysis. Okay, so for today and tomorrow, we're simply talking about single subject analysis. That's also called first level analysis. All right, so when you hear the term single subject or subject level or first level, those all mean the same thing. It's you have 10 minutes of fMRI data. What do you analyze? How do you analyze it? And what are you hoping to get out of that? So if you look at so the idea here is in red we're showing, for example, in this scan here we're showing that if you have a hemodynamic response with a stimulus, let's say we just hammer it with a very short, brief flash of light with an amplitude of 1, you're going to get this response. Okay, so the hemodynamic response is, for those of you who are more techie, is what's called the impulse response. It is the response of the brain to a very brief stimulus. Okay, and how have we measured this? Mostly through visual experiments where they just give a brief flash of checkerboard and they look at the response of that. Okay. So one property that people have found is that if you then double the stimulus, like you double the contrast of the visual stimuli, then the response goes up by a factor of 2. So if you double the input, the output doubles. So that's one aspect that people have observed. People have also observed that if you hit the brain, say at time 1 here with a stimulus, and then you come over at time 2 with another stimulus, the response to the first stimulus is shown by this green curve here. Okay, so that's the response to the first stimulus. And the response to the second stimulus is approximately the same. Okay, so that's another property that people have observed. Okay, the other property people have observed is if you have those two stimuli, then the response to those two stimuli is actually simply the sum. So I would take these two stimuli and sum them up, and then I get what's shown in the blue curve. Okay, so if I have two stimuli, I can look at the response to each stimuli, and the response to the two stimuli is simply the sum of those two responses. So that's what's been observed, and we'll show you some data on that. But those are the properties that underlie what are called what's called the linear time invariant model. Okay, so we have linearity, and we have time invariance. And all that means is exactly what we just said. One part of linearity is if I scale my stimuli, so I scale it from here, say a factor of 2, but it could be a factor of anything. If I scale my input, then my output scales. Okay, so that's good because if you're doing fMRI, that's a pretty basic assumption we're making, right? If the brain is working twice as hard, we would hope that the bold signal would go up about by a factor of 2. Now, it's not always going to go by a factor of 2, but this sort of, it's going to go by some factor, but the idea is to first order, we assume that things scale with the difficulty or how hard the brain is working. All right? The other aspect of linearity is the summation. If I have two inputs, okay, then the response to those two inputs is going to be the sum of the responses of the individual inputs. So that's shown by this blue curve being the addition of these two green curves underneath it. Okay, so that's that summation. That's a fundamental thing that's going to be built into all our analyses. We are going to assume that the brain satisfies those properties. Okay, and the final thing is time invariance, which we said that if I excite the brain at this time, it gives me the first green curve, and if I excite the brain at another time, it gives me the next green curve. And if the shape of those curves is the same, then we say the brain is time invariant. Okay? So it would be rather remarkable if the brain satisfied all those properties, because if it did, then we can make use of 100 years of work in electrical engineering and signal processing and statistics and adapt all that machinery to fMRI. Okay? And luckily enough, it turned out the brain actually does, it's a good approximation for the brain, which means we don't have to reinvent all that sort of math and theory that's been invented by lots of people over the years. So a lot of fMRI is based on their very deep statistical and electrical engineering work that's been done previously, and it's just because the brain seems to satisfy these properties, we're allowed to use these approximations. Right? So this was actually a very seminal paper by Jeff Boynton, who used to be at the Salk, and this was work he did when he was a grad student or a postdoc, I believe, at Stanford. And just showing, this is basically written before most of you were born, or some of you were born maybe. But this was a seminal paper because it basically showed that you could approximate the fMRI response using these properties that we just talked about. So for example, this is response to visual stimuli at different contrasts, 0.25, 0.5, and 1. And you can sort of see the brain response scales up. Okay? And then they use different durations, 3 seconds, 6 seconds, 12 seconds, and 24 seconds. Okay? And if summation works, then you should be able to use, for example, the response at 3 seconds, and then if you just sum it up with a delayed version of it by 3 seconds, add up those two responses, you should be able to predict the response at 6 seconds, of a 6-second block. Similarly, if I know the response at 6 seconds, well, 12 seconds is just that twice, right? So if I sum up the 12-second response, 6-second response twice, I should be able to get the response at 12 seconds. Okay, so that's exactly what they did. Whoops. Why isn't it letting me move? Okay. So this was the 6-second response. So this is the prediction using the 3-second responses. Okay. So the solid curves are actually what they actually measured. Okay. And then the light curve is what they got if they took a 3-second response and then just shifted and summed those responses to predict the 6, the 12, and the 24-second responses. So this is rather remarkable in the sense that actually, to first order, the brain is actually satisfying these summation properties. Okay? And the fact that it does is it sort of underlies all of the subsequent fMRI analyses. All right? So this is just sort of showing you that, you know, what we're doing is based on primarily this piece of work. There are other pieces of work, but this is really the seminal piece of work that really let the field proceed and say, okay, we can use all these models. Okay, so for most of this lecture, then, we're going to assume that the brain follows these properties. And if it does, there's a process that's called convolution. We're not going to get into the details. It's a mathematical operation. But it just basically is, if you can think of it as, this is the hemodynamic response function, okay? And this is my stimulus. I this operation, which you'll hear about when you read about FMRI, but you don't necessarily need to know the details, is called convolution. You can think of it as just sort of taking the stimulus and smoothing it by the shape of that hemodynamic response function. And so typically the output, so here is the output if I take that and do that convolution. And it sort of looks like my input, but as you can see, it's delayed a little bit because this has some delay to its peak, right? And also it's smoothed out a little bit because this is sort of a smooth function, whereas this has a lot very sharp edges. All right. So for the purpose of this course, you just need to know that a lot of under the hood, the software is doing this for you. Okay. This is typically what you'll enter. You'll enter in some timing, saying my stimulus was on, it was off, it was on, it's off. You might pick some parameters of your hemodynamic response, but generally, if you don't, the software will default and it will just do this for you. So what it enters into the analysis is not, it doesn't enter this. It enters in the red curve, okay, because that's what it thinks the brain is going to be doing. All right, the brain, it can't go on and off instantaneously, right? So the hemodynamic response function means it goes up. It generally takes a few seconds to go up and maybe then a few seconds to go down. All right. So this red curve becomes what's called your regressor, okay? Or another term that the FSL folks like to use is your explanatory variable. Explanatory variable. So in FSL world, if you see the term EV, it stands for explanatory variable. All right. So that's the first concept, is that you will be entering in, when you do these practicals, you'll be entering in the stimulus timing and sort of what stimulus is shown when. The software will do this convolution for you so you don't have to worry about it. Any questions? So here's a general experimental question you will be typically asking is, first of all, which voxel in the brain have a time course that looks like that? Okay, that's the expected response to my stimulus. So first of all, I want to know where there might be some voxels that are showing a bold time course that goes up and down like that. But I also might want to know, well, you know, for which of those voxels, for some of those voxels, it may look very weakly like that. For other voxels, it looks really like that. So then I want to have some way of statistically assessing whether it's significant or not. And then at the end of the day, I want to create a map. And in this case, it's a thresholded map here shown on sort of a visual, a 3D display. So that's what we're really going to talk about today, is just sort of some of this will be review for some of you, others it might be newer. Okay. So here's the experiment that is, and a lot of these, some of these slides, the FSL course has really nice slides, so you know, where I use those slides, they'll be referenced down at the bottom, so you can always take a look at the full slides, but I'll mix it, I sort of take from different sources, so you'll always be able to see the source at the bottom typically. So this was something where, so we'll use this experiment for several of the slides. So the experiment had two main tasks. There was a word generation task and a word shadowing task. If you go into those slides, I'll tell you more about those tasks were. And then there was something called a null event. Okay, so that's something you'll hear when you talk about, when people talk about fMRI experiments, a null event. Okay, so what is that? A null event is typically, it's somewhat controversial, but it's used quite a lot. And a null event is simply where you don't have the subject doing anything. So for example, in this one, they might be showing words during the word generation and word shadowing events. During the null event, they might just be showing a blank screen, okay, and sort of letting the brain rest, right? So let's say, let's look at sort of what we're going to do. The first thing that we're going to do in any software is we're going to tell the software when the timings of each event were. Okay, so for example, for the word generation, let's say the event timings were represented by these bars. So everywhere there's a bar, I showed that a picture of the word generation. All right. So the software takes that, and for each of the events, you're going to give it some information like that. It's going to then convolve it with your hemodynamic response function. It's going to have this sort of nice response, brain response. Okay. Typically, it's going to do this at very high temporal resolution because your timing might be at hundreds or 200 or sub-second timing, right? Okay. But so this prediction of what the brain is going to be doing can be done at fairly high temporal resolution. But typically, you're not acquiring your data at every 100 milliseconds. Okay, the fastest we typically acquire now is about 800 milliseconds, but older designs might use 2 seconds. So the next step is the software will subsample it. It will take this high resolution and just pick out different points of this at a lower resolution, and that's what you're going to use for your final regressor. All right. So that's why it's important. So this is basically, it has to know what your TR is, so your repetition time. So once it knows the repetition time, it says, okay, well, your data weren't collected at this high resolution. It was actually acquired at this TR time. So it uses that information then to subsample your data. Right? So then this is the basic scenario we have. We're going to have, for every voxel, we have some observed data. And then these are the two regressors we have. We have one for the word generation and one for the word shadowing. And we're going to say that we think that the observed data is the sum, at every point in time, the observed data is the sum of these two regressors. Okay? And so these are the EVs, the regressors, the explanatory variables. But what we're going to do is we're going to figure out, what we're going to try to estimate is the size of these beta coefficients. All right? And so the idea is, let's say this is an area in the brain which is mostly responsive to word generation. Then we would expect beta 2 to be close to 0, right? Because if it's not related to word shadowing, just word generation, and we expect this to be greater than 0. Okay, so that would be those regions. And similarly, if it was a region in the brain that was related to word shadowing, we expect this to be greater than 0 and this to be close to 0. And there may be large regions of the brain where it's not related to either one, in which case we'd expect both to be equal to 0. All right, so that's what we're going to go after. We're going to say, how do we estimate these beta coefficients? And then how do we assess whether they're statistically different from 0? So the null hypothesis, which we'll review a bit, but just to preview, most of you know what it is. The null hypothesis is beta 1 equals 0 and beta 2 equals 0, that there's no activation. Okay, so now we want to see, is there sufficient information to reject the null hypothesis in that voxel? So for today, we're going to go, every voxel is going to be analyzed independently. Okay, so what we're going to do today is what's called mass univariate analysis. Okay, so a lot of fMRI, even to this day, is still done with mass univariate analysis, where every voxel is treated independently from every other voxel when we analyze it. Now, there will be some exceptions to that rule. For example, later on, towards the end of the course, we'll talk about things like independent components analysis, which is sort of multivariate analysis, and there are other things. There are other forms of multivariate analysis as well, but by far, most of you will primarily be doing mass univariate analysis. Okay, so this is just to remind us where we're at. So this is the FMRI time series over here. These are our model regressors. And for every voxel, we're going to try to estimate these beta values. Okay, and so here, they're both about 1. Here, 1 is 1. Here, it's close to 0. And here, they're both close to 0. And then typically what you do, one thing you can do is you can display these beta maps. So this is the beta 1 map. This is the beta 2 map. And that gives you a sense of how the brain is activating to the different stimuli. So where it's very bright, you could say, well, that might be related to word generation, and vice versa. So that's part of the picture. And then what's going to be done is actually these beta maps are typically then what goes to the next order of analysis or the second level analysis. Okay, which we're not going to talk about until sort of a few weeks down into the course, a few weeks later, and that's where it is the group analysis. Okay. Next question.
beta is, like, beta 1 beta 2 is referring to the different stimuli in your
Yeah.
cell. How come we don't include anything for the null event? Because there would still be something going on for that, right? Or?
Yeah, that's a good question. So the idea is that we need to have the null event. If, for example, if you just had one stimulus, right, like it's either null or off, then you just 0 or 1 represents that.
Okay.
But you could represent it with -1 or 1. So it just turns out mathematically you need something that is sort of where there's no stimulus on. So the null event is saying there was no stimulus on. So that's represented by a 0.
Okay.
Yeah. Now, with the whole, so even before resting state fMRI became big, there was some question about whether the null event is really a null event. Maybe it's actually doing something. So that's still a concern, but in general, people just ignore it because it's just easier to ignore it. And that a lot of fMRI is just, we should worry about it, but if we worried about everything, we would never get anything done.
Yeah.
So we selectively ignore certain things. Yeah. Okay. But for certain experiments, you may not be able to ignore it. So if you're looking at your data and you're like, hey, something's really happening in this null event, then you may need to model it differently. So for example, Craig Stark, who used to be there, sort of had a whole paper about the null event not really being null. Despite that paper, people still ignore it. Yeah. Okay. So the next thing we'll talk about is this thing called residual error. Okay. So a model is just a model, right? That regressor is what we think the brain's going to be doing. The brain's obviously not going to be doing exactly what we think it's going to be doing. Plus, there's going to be a lot of noise sources, which we'll talk a little bit more about next time. But there are things: the subject's moving, they're breathing, they're generally alive, right? So their heart's beating, and plus there's noise from the scanner. And so essentially, the residual error is basically the difference between the measured data and your model. Okay. And so what we're going to use to do is we're going to use that to calculate what's called the variance or the noise. Okay. And that's going to be used to calculate our statistics. So the residual errors is sort of essentially that part of the data that we can't explain. Okay, so this is a picture of where we're headed towards. So this is now describing our general linear model. And so we will be using sort of matrix notation, right? Because that is the standard in the field. And we're not expecting you to do a lot of things with matrices, but I think if we didn't show this notation, it sort of wouldn't be fair, because when you're reading papers or looking at textbooks, they all use this notation. So it's better that you just bite the bullet and you get some level of comfort with this, at least interpreting what the matrices are and what they look like. Okay. So in general, if something is a vector, which means it's either a very long column or row, we'll use lowercase. So for example, this y is my vector. So I can imagine putting all those values into a long thing. Okay, and those are just numbers, right? Every point in time, there's just a number of data. This is my design matrix. Okay, the design matrix basically encapsulates everything about my experiment. Okay, in this case, it's capturing the response to event 1 and event 2. And so typically, each column in your design matrix is going to be responding to each stimulus type. Okay, and this is actually most of the software, I believe all the software, FSL, AFNI, even SPM, they typically will display the matrix as this sort of, this black and white behind it, where you see sort of the on or off. Well, you'll see that a lot in all fMRI software, where it's just basically showing you in graphic form what that matrix looks like. Okay, so typically where it's bright, you have an event, and where it's not bright, you have no event. And in this case, I believe they're not only showing you the timing, but the red is also showing you sort of what the convolved response would be. Okay, so it's showing what it looks like after convolution. The next thing you're going to have is your beta coefficients. In this case, we have two events, two stimulus types. So we're going to have a beta 1 and a beta 2. Okay, we're just going to stack those into a vector. And then we have E, which in this slide is called Gaussian noise, although typically it's not necessarily Gaussian, but we'll better call this sort of the residual error. All right, so that's all the general linear model is. Today we're going to go over the simple form of that. On Wednesday we'll make it slightly more complicated and add sort of nuisance regressors and confounds and other things. Today we're just going to focus on what happens if you just have the brain response. Okay, so this is just rehashing that. And so the goals is that, so in general in science, no matter what you're doing, you always have data, you always have a model, and you always have error. All right? And in general, you're just trying to estimate the parameters of your model. Okay, you have some model of the world, you want to estimate the parameters from the data, and then you want to assess the statistical significance of those parameters. So the generally a model is a very specific case of a model, which is used everywhere in science. And part of the reason is because it's really easy to, because there are solutions for it. Okay, there are much more complicated models, but the more complicated model is, the harder it is to analyze. So since the brain, to first order, acts like a linear system, it's appropriate to use a general linear model. Okay, so let's talk about general linear model for something that's a little simpler, because FMRI data, are quite complicated, and so it's actually a little easier to get these concepts using a much simpler model. This is from the appendix that's part of your assignment reading. So this is part of the FSL primer appendix. So you can feel, that you'll read that primer as part of your reading for this week, but this is one of the figures from that. So it's a very simple example where we're measuring the height of 5 people. Okay, so what would be an appropriate model for this? Well, if these were all sort of, so one hypothesis what we might want to do is say, well, we think we can model this as everyone has some average height, and then there's some deviation from that average height. Okay, so everything in this vector, the y's would be the heights. Okay, we measure heights. Our model is that everyone has the same height. Okay, we're saying everyone has the same height. So that's the ones. There's a 1. And then this beta, what would be our interpretation of the beta? If I estimate beta, what would beta represent?
Deviation from the average height.
Okay, so one possibility is the beta could be the deviation from the average height. Okay, so this is the beta shown here, right? So the beta, so these average heights are equal to beta, 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 plus these terms. So what might be another way of looking at what beta should be? How do we interpret what beta is? Beta is the average height. Yeah. So if you think about taking these things, then beta is sort of, each of these it's saying like, this is equal to beta plus some error. This is equal to beta plus some error. Each of these heights is equal to beta plus some error. So beta must be the average height. Okay, so beta would be the average height. Okay, and these are the errors. Okay, what must those errors sum up to? If beta is the average height, what are all the errors be equal to? 0. They all have to sum equal to 0, right? So the sum of those equals 0. Okay, so even though it's really simple, those are really key concepts, right? That the residual errors all sum to 0. Okay? Otherwise, it's not going to be the average, right? There would be some other number that would get it to be 0. Okay, so so our goal is to find the beta hat. So we'll use the hat notation to bring an estimate. Okay, so beta without a hat is sort of, what nature decided, and and our guess of beta is beta hat. All right, and we're going to use the beta hat that minimizes what's called the residual sum of squares. So it's E1 squared plus E2 squared plus E3 squared plus E4 squared plus E5 squared. Okay, so basically each of these deviations here, that's like E1, E2, E3, E4, E5. So the distance between each of those dots and the line is the error. Okay, we're going to take each of those little deviations, square it, and then we're going to sum up all those squares. Okay, This is similar to some of you have heard of like minimizing the mean squared error. Okay, same thing. And then just as a sort of a note, beta hat is also in FSL is called parameter estimate. So when you see the initials PE in FSL, this means beta. Okay, parameter estimate. Okay, so we're not gonna use. I'm gonna tell you what the result is, but I don't. Rather than just pull it out of thin air or say it's lots of algebra, I want to at least give you some concept of how you can think of these things geometrically, because I think it is useful to have this in mind. So any vector, any sort of vector, okay, is just a bunch of numbers, right? So like this is a vector in two-dimensional space, so this would have some coordinates a, comma b. In general, for fMRI data, I might have 100 or 200 numbers, and that's just some vector in some very high-dimensional space. But we can't really think about things in more than 3 dimensions, so it's actually sufficient to think about things in 2 dimensions. So y is going to be some vector, which is just a bunch of numbers. So for example, in the previous example, it's just my heights. Then x is some other vector with the same number of dimensions. So in the previous example, it was just ones, right? And so in all of generally model, we're going to say, what can I multiply x by? You know, sort of what is the length? This is x, and x times beta hat is going to be some scaled version. So I could have a very small version or bigger versions of x. But I'm looking for that special x times some number that minimizes the length or the error. Okay, and so you can sort of see that that length is minimized when this is perpendicular. Okay, because any other choice would have a longer length, right? Any other choice has a bigger error. So all that means is my best solution will be when I choose the x beta hat, I choose the beta hat such that x beta hat is perpendicular to my error. Okay, and then mathematically that means it's orthogonal. Okay, so my error is always orthogonal to my model. Okay, so with that in mind, we can write down, so this is the only math matrix algebra we're going to do today. This is my error. Okay, that's my error. It's the data minus my model. And then x transpose of that is just, this is how we describe orthogonality in matrices. X transpose of this is equal to 0. This just means that's how we say things are orthogonal. Okay? And if I solve that, I can get what's called the least square solution. So I can estimate beta hat from the design matrix times my data. Okay? So software is doing. Okay, so AFNI, FSL, SPM, they're all doing this exact mathematical operation. Okay? So you have to supply the data, and you have to tell it something about the design matrix, which is typically just what was the timing. Okay. Okay, so if I do that, and if I plug in all those things and using this general linear model, I get that beta hat is just the sum of y1, y2, y3, y4, y5 divided by the number of samples, which is in this case is 5. So it is indeed the average height. Okay, so that's basically just saying that even though it's a complicated looking equation, for this very simple example, it's going to give you exactly what you'd expect from intuition, is the best estimate of beta is your average height. Okay, so now we have to talk about test statistics, all right? Because we need to know whether beta hat is actually significantly different from 0. So in general, test statistic is always going to be a function of 2 things. It's going to be some function of your estimate and some function of the covariance of your estimate. So this is sort of a measure of how noisy is your estimate. So I could give you an estimate, but if it's like if I said, well, I think the average height is, let's say we were measuring, I don't know, worms, all right? So I think the average length, I measure the average length of the worm to be 3 centimeters. Okay, so you're like, okay, that's pretty good. But then you ask me, well, what's the standard deviation of, what's your error? I say, well, the standard deviation of my measurements was like 10, right? Or 5, or it can't be 10. Well, let's say it's 2, right? So I measured 3, but I had a standard deviation of 2, right? And I only measured 3 worms, okay? So intuitively, you know that probably that's not statistically significant, right? Okay. So we need to just sort of now talk a little bit more about or review how we actually assess statistical significance. And so, for example, most of you are familiar with the t-statistic. So in this case, the t-stat would just be equal to the estimate of my mean height divided by the variance of my estimate, okay, which is different from the standard deviation of the heights, okay? It's the variance of the estimate. So it's actually the estimate of my mean height or the standard error of the mean, okay? So some of you may have seen this, so that's typically abbreviated SEM, okay? So t-stats are always going to be beta hat over the standard error of beta hat, okay? It's a measure of your estimate divided by the standard deviation of that estimate, okay? So let's look at that. So basically, the main things we're going to do is every statistic can be written in this form. Okay, and you don't need to be responsible for the math, but I'm just going to use it to show how we're going to get there. And then what we'll do is for the exercises, we're going to be more applying on how do you understand and use it. So let me just say that every statistic is going to be related. You're going to see beta hats in them, and you're going to also see the covariance of the beta hat. Okay, in general, and then this is inverted. Okay, it's always going to be something like where there's signal on top and noise on the bottom. Okay, so always a signal-noise ratio. And this covariance is always going to have something that depends on your design. Okay, and then this sigma squared. Okay, and this is what's called. This is going to be referred to as the sample variance. Okay, so if you look, for example, on Wikipedia, oftentimes it's just called S squared. Okay, or I think, is it S squared or S? I forget. It's either S or S squared, but typically you'll see that. Does anybody know offhand? It's just S, right? Okay. Let me try to erase that. Erase that. Whoops, I erased too much. Okay. Let's see if we can.
Sample variance, I think, is still after S squared.
Is it still S squared?
Yeah.
Okay, well, we'll check on that. All right.
Looks like it according to Wikipedia.
Is S or S squared?
S squared.
S squared. Okay, so sample variance is S squared. Okay. Yeah, that's right. And then the sample standard deviation is just S. Okay. So so you'll see both. So the sample variance is actually equivalent to this theta hat square. So typically the covariance is dependent on sigma squared, which is what's called the true variance. Like if you knew what the variance was determined by nature, then you could use it, but we don't know. So we always have to use what's called the sample variance, and we have to estimate that sample variance. Okay? And the way we estimate that sample variance is by taking the residual sum of squares and dividing by the degrees of freedom. All right, and so we're going to talk a little bit about all those terms in a bit, but this is what it looks like. The sample variance is here, and it's equal to all those error terms squared. So that's just the sum of those is just the residual sum of squares, and then we're multiplying, or we're dividing it by the degrees of freedom. Okay, because we're trying to figure out how noisy, what is the size of the noise, all right? Okay, so let me see, get rid of that. Oh, there, that's how I get rid of it. Okay, so let's talk a little bit about degrees of freedom. And so if a data has n dimensions, so typically I'm going to have the data is y, and let's say it has n dimensions to it, okay? And it's going to be equal to some x times beta, okay? And this is typically going to have dimensions of n by k, okay? So if I had like k different stimuli, I would have k columns in X. Right? Then in that case, the degrees of freedom is always equal to n minus k. All right? And so, for example, to sort of get that across, basically, if you sort of see, if this is my data y, right, and I said the best estimate had to be x beta such that the error was orthogonal to my model, this means that E only has 1 degree of freedom. It has to lie on this line. Okay? So in this case, the degrees of freedom is 2 minus 1 equals 1. Okay? Because y could be any two numbers, a comma b, but E can't be any vector. It has to lie on that line. Okay? So once we've just defined our model, we've taken away degrees of freedom for what that error term could be. So that's what degrees of freedom means when you're looking at statistics. And for example, in this case, y could be a three-dimensional vector, a, b, or c, but E has to be perpendicular to this two-dimensional plane because now x has 2 dimensions. So here, the degrees of freedom is d of f equals 3 minus 2. Once again, it's just 1. Okay, the error has to lie in this. Okay, but so anytime you see a design matrix and you're wondering what the degrees of freedom are, it's just going to be n minus k. And even though a lot of times people ignore degrees of freedom and just report t-stats or p-values, I would encourage all of you to start reporting. If you're reporting a t-stat, it's meaningless unless you report the degrees of freedom. Okay? I mean, you can always report the t and the p and then let the reader go back and work out the degrees of freedom, but it's just much easier. You can just say t with this degrees of freedom was equal to that. Right? Okay, so for example, in our example, we had 5 elements of our data. So the data dimension was 5. The model dimension was 1. This only had 1 column, right? So the degrees of freedom was 4. They're the error. Okay? And how can we think about that? So that's saying that these 5 numbers, E1 through E5, only have 4 degrees of freedom. Okay? And think about it. Because we said that the sum of those numbers has to be equal to 0. Right? So once I know the first 4 numbers, then the 5th one is determined for me. So there's only 4 degrees of freedom. Right? I don't have total freedom to select all 5 independently. So that's another way to think about degrees of freedom. So in this case, if I know the first 4, then the 5th one is just equal to that. Okay? They have to sum up to equal to 0. So anytime you have a model, you're putting a constraint on what the error can look like, and that's where that degrees of freedom comes. Okay, so are there any questions? Okay, if not, let's. Okay, so go ahead and open up Canvas, and you can have access to open it. Okay, let's take a look. It looks like everyone's getting the answers right. So let's just take a look at the answers. So the first one is has 4 minus 2, so it has 2 degrees of freedom, right? So that would go with B, right? The second one has 1, 2, 3, 4, 5, 6 data points, minus 3 columns, so 3 degrees of freedom. And this one is 1, 2, 3, 4, 5, 6, 7, minus 3 equals 4 degrees of freedom. Right? So anytime you look at a design matrix, you can see exactly what the degrees of freedom are going to be for the statistics that you're doing. All right? Okay. That's for a t-stat. It's going to be a little different for an F statistic, which we'll do later. All right? Okay, so let's look through that t statistic. So general form for a statistic has this on the top and the degrees, the RSS divided by degrees of freedom on the bottom. And if we work through that for this example, and we say that t equals the square root of our general t statistic, then what we end up with is our average height estimate times the sample standard deviation divided by the square root of n, which most of you know as the standard error of the mean. Okay, so this is the mean divided by the standard error of the mean. And essentially what you're probably familiar with from other courses on what the t-statistic should look like. Okay. So in FMRI, what we do then is instead of having a simple regressor like that, we might have a more complicated regressor like this. This is our data now. And then what we do is we find the beta that scales that regressor such that it best matches our data. And then the red here, these are sort of those little bars that you can sort of see better here. Those are our error terms. Okay, and so taking the beta sort of and dividing by its estimate of its covariance, and that's going to be the t-statistic. And once we have that, then we review what we mean by hypothesis testing and what thresholds we want to have. And so typically in FMRI, there's a lot of one-sided testing done. Typically, if you're looking to doing a scan session, there's activation. Typically, something where you're just looking for positive activation, but you might also look for negative activation. Okay, and then if you don't really care about the sign, then you can do a two-sided test where you're just looking for B is not equal to. Okay, so in all of those cases, you're always going to be looking at the null distribution, which is basically the distribution of the t-statistic under the assumption that beta is equal to 0. All right? And so if beta was equal to 0, then there's always going to be some probability that for example, in this case, if the probability, if you want a 0.05 significance level, if you're out here, okay, then the probability is less than 5% that you would have seen that value by chance. Otherwise, so you would reject the null hypothesis. So only unless you're sort of in those tails of your null distribution can you reject your null hypothesis. Okay. So I'm just going rather fast because I'm assuming this is a review for most of you. But that's generally what is done is once you have the t-stat, you will set your threshold level and say at 0.05, you'll have different thresholds. So even though people don't use tables anymore, I thought it's useful to bring it out for purpose example. So if I'm doing a one-tailed t-test and I want 0.05 significance level, you can see I need a t-value of around, as I get really large numbers, around 1.6. Okay, and that number, as the number of degrees of freedom of the t-statistic goes to infinity, the t approaches the z, or the t distribution approaches the normal distribution. So that z value is basically almost the same as 1,000 degrees of freedom. So for a one-sided t-test, you know that about 1.6 is good enough for having statistical significance. So even without doing anything, when you're looking at your data, you can get a sort of good sense of, okay, t of 1 is basically the signal and noise are about the same, right? So I need to have that value threshold be about 1.6 before I can pass a one-sided t-test, all right? If I do two tails, the threshold is slightly larger. You can sort of see here, I need about 1.9 or about 2. Okay, so that's really a good rule of thumb. Basically, in general, for most things to pass a 0.05 threshold with a t-test, you're looking for t's around 2. Anything less than that, and you're sort of fooling yourself into thinking that you have an effect. Okay, t of 2, t of 3 is good, great. So what you really want are t's of 3s and 4s. If you're down around t's of 1 or 1.2 and 1.3, and you're trying to like eke out an effect, you're sort of you maybe need to stop and make sure you're not doing something dangerous. Okay. Okay. So that's basically what we're doing. We're taking our data, we're looking at our residuals, we calculate our t-stat. In this case, we get a t of 1.86. It's a one-sided test. It's greater than our threshold of 1.68. We're like, okay, great. We're below the 0.05 threshold level. Okay. And for many years, people were very happy with the voxel-wise level, especially when we did their group analysis. And even today, if you're just looking at your data and you want to get a sense of whether there's activation, it's fine to do a threshold of 0.05. But when we talk about group analysis, we're going to see how in the last few years, the field has really moved away from 0.05 thresholding for rigorous work. So if you're going to publish your work at the group level, you're going to have thresholds down at 0.01 to be convincing. Otherwise, 5 years ago, you could have published your paper. Today, you probably can't publish that same paper. Okay? Okay, so basically, for single subject analysis or single scan analysis, we have our FMRI data, we have our statistical map, and then we might threshold it. And typically, what you're going to use this for when you're looking at data, you're just trying to get a sense of how well the data looks at a single subject analysis level. If you have a very strong design, you're going to see nice activations. But oftentimes, you're not going to be able to see this at the single run level, especially if you're looking at a very subtle effect. And it's not until you do your group analysis so that you're going to be able to see this. Okay, so this is much more a sanity check for you to sort of see, or if you have a very strong stimulus and you know that it should light up these areas of the brain, then this is something that you can do as a sanity check at a single scan level. Okay, so now let's sort of broaden our scope to, we need to talk about when there's more than one regressor, okay? Because we want to talk about, we'll spend the last 20 minutes talking about contrast vectors, because that's the other thing that you need to be comfortable with in terms of dealing with the different software. So we'll actually have 2 exercises on contrast vectors that we'll try to get done today. So in this case, I've got 2 groups, okay? And so I'm trying to estimate the height of group 1 and group 2. So we have 2 estimates, beta 1 hat and beta 2 hat. And therefore, you might think about, now I have 2 numbers, so I could sort of think about different ways of looking at those 2 numbers. The first thing I'm going to do is I'm going to estimate. And so if I go through the math and estimate it, lo and behold, the estimate is just the average height of group 1 and the average height of group 2. So no surprises there. Okay, the math does what I think it should, and so that's good. But now what I want to do is I want to introduce this concept of contrast vectors. Okay, so we're going to take beta hat, actually multiply it by this contrast vector. And for most, typically that contrast vector is going to be a row vector because the beta hat was a column vector. So in this case, let's say the contrast vector is defined as 1 minus 1. Okay, so 1 minus 1, and I multiply it by beta 1 hat, beta 2 hat, and that just gives me beta 1 hat minus beta 2 hat. So this is now a contrast of that beta 1 hat minus beta 2 hat. So it's like, are the heights different between these 2 groups? So when we do 2 sample t-tests, this is exactly what we're doing. Okay. So now my statistic is going to be able to form, instead of beta hat, it's C beta hat, and it's the covariance of C beta hat that I'm looking at. All right. So I'm going to be looking at not just beta hat divided by its covariance, but I'm going to be looking at C beta hat divided by the covariance of C beta hat. Okay, that's what I'm going to care about. So if I go through this example, I get the t-statistic is equal to beta 1 minus beta 2 hat divided by this formula here. And so this has got this has the form of the sample standard deviation And then I've got the number of samples in group 1 and the number of samples in group 2. This is a formula you've probably seen in your previous statistics classes. This is just showing that you can get it by just looking at, using these formulas. Okay. Okay, so let's instead of focusing on that, let's really talk about what this means and how do we interpret it. So basically the idea is we're going to look at our difference here, x1 minus x2 hat. This is our sample variance. And then this here is telling us sort of how many measurements we have. Okay, so the statistic, the more measurements you make, always goes up. Okay, and that is sometimes why you can have the same t statistic. In one case, it's significant. In another case, it's not significant, depending on how many samples you had and how many degrees of freedom you had. Okay, so in FSL lingo, this contrasts, and the other thing that you'll find is not consistent is sometimes they'll call it C transpose beta hat, and other times you'll have C beta hat. So it depends on whether C is a column vector or a row vector. So you'll just be aware that that's not consistent. So the Poldrack book, I think, does it one way. The FSL notes do it another way. All right. But in any case, that contrast is what's the FSL groups call that a contrast of parameter estimates. So when you hear the term COPE, that's what we're talking about. All right. In AFTI lingo, it's referred to as a GLT or a general linear test. So when you're asked to specify your GLT in, say, 3D deconvolve, which is a program we'll look at for the next practical, that's what we're looking at, these contrasts. All right. Okay, let's take a look at this. So this is basically, we have two cases, sort of word generation and word shadowing. And if I had 1 and 0, this would just pick out the first explanatory variable, right? So 1, 0 times beta 1, beta 2 hat would just give me beta 1 hat. Okay? So if I see a 1 in the first place and a 0 for the second one, that's just going to look at the first variable, which is baseline. If the 1 is here, that's going to pick out the second variable. If I have 1 and 1, that's going to take the 2 and add them together and say, is the mean of my two responses greater than 0? In this case, I've got minus 1 and 1, so that's saying, is this minus this greater than 0? So in this case, is beta 2 hat greater than beta 1 hat? Okay? And this would be, is beta 1 hat greater than beta 2 hat? All right? So this is when you're specifying contrast matrices, you're basically able to specify all these different tests. Okay? So rather than specify each of these as a different general linear model, what people have found is much more useful is you put all your explanatory variables in one general linear model, and then you use your contrast matrices to define what tests you care about. Okay? There are other ways of doing that, but this turned out to be the best way to do it because it's the most generalizable. All right? Okay, so our question will give you this exercise. Okay, so let me just explain this exercise for you. So in this case, treatment is your explanatory variable 1, so it's related to beta 1 hat. Control is variable 2. On this side, you have contrast matrices, and on this side, you have the description. So there's 7 of those, and you have to match each one. Okay, so let me go ahead and open up that quiz. Okay, so that should be visible now. And feel free to discuss. This is just, it's not graded for accuracy. It's just graded for completion.
Do you prefer looking at this side first and then see? Is that what you yeah, so it's really good. Okay. That's what I think. Yeah. No. No, patient control. Yeah, just in there at risk of patient group is okay. That's good. I was like, patient control. Yeah. Okay. What's remaining? No, I just hope that he really has that treatment is first one, but whatever.
Okay, looks like most people responded. So I think let's just take a look at it. I think most people got this, but it's useful to go through it very quickly. So 1, 0 is obviously the mean of the patient group is positive, right? Okay, because selecting the first one. And then this one is the mean of the control group is positive, right? Because it's selecting the second one. The third one is 1 minus 1, 1. So that's when the control group is greater than the mean of the patient group. Is that right? Okay. And then similarly, this one is just that one. And the minus 1, 0 just means it has to deal with the patient group, and so it's the mean of the patient group is negative. Okay. And then this one is here, and this involves both, so it's the mean across the groups. Okay. Are there any questions on that? Okay. So it's fairly straightforward, but it's useful to know that this is what you'll need to do for contrasts. And so, yeah, so this is reminding us that when we have two contrasts, we have two regressors here, and we're solving for the beta 1, beta 2. Okay. So the last thing we want to talk about is F contrasts. So when would you use a T-stat versus an F statistic? And so here it might be that you're just really looking to see, did anything happen? Okay, so I used I had these two conditions, or I had three conditions. This is the first time I've done the experiment. I really don't care about, you differentiating the contrast between the variables as a first pass. I really just care about whether the brain did anything in response to any of these conditions. Okay, so that's where you use an F contrast or an F statistic. One thing so that's really, is there activation to any condition is where you might use it. Does any regressor explain the variance in the data? So where this could happen is significant if, for example, each of the regressors sort of responded a little bit, okay, or a medium amount, or it could even be one responded a lot and the others didn't respond very much. So the F statistic doesn't really tell you which was the strongest. It just says overall there was enough activation that something significant happened across all these different conditions. All right. And one thing about it is the F contrast is not directional. So it's more similar to your two-tailed t-test. Okay. So let's take a look at an example of this. So for example, this would be the contrast matrix for this design to do the F statistics. So if I had this, you see it's got 1, 0 on the first row and 0, 1 on the row. So like this is just the identity matrix. So if I multiply the identity matrix by any vector, I just get that vector back. So this is testing the contrast. It's saying, is beta 1 equals 0 and beta 2 equals 0? That's my null condition. And the alternative hypothesis is that beta 1 is not equal to 0 and beta 2 is not equal to 0. Okay, but it turns out that there are different ways of becoming significant. As I said, it could be that beta 1 is really different from 0, and beta 2 is not that different from 0. I could still have a significant F statistic. Okay, so let's take a look example of a. So this is going to set up us for our next exercise. So in this case, we have 4 explanatory variables. So we have left foot, left arm, right arm. Okay, and so these are the regressors for the different conditions. And so this is what the design matrix looks like. Here's another example from an SPM thing where it also has 4 explanatory variables. And in this case, the 4 variables are here. And all these other 7 variables are confounds, which we'll talk about on Wednesday. So in this case, the F matrix looks actually different. You've got each of these rows is picking out the variable you care about, and then you're having zeros for all the things you don't care about. So this would be a contrast matrix, which would be for an F statistic, where you're saying, did any of my stimuli give rise to an activation? Okay. Whereas, okay, so this is our second exercise. So basically, let's see. So in this one, it's a multiple choice. So for both of these questions, let me publish the quiz now. You're going to be given a choice of what different contrast matrices might actually satisfy each of those questions. And let's publish that now. Okay. So go ahead and take a look at that and feel free to discuss. Okay, let's take a look at that. If you're still working on it, you can still submit your answer, but in the interest of time, we're towards the end of class. So this one is asking which brain regions activate more to pinpricks to the left than the right foot. So it's acting in a specific contrast. So we know we're going to just be giving it a single vector. So it's going to be for a t-statistic, right? So this would be either a COPE in FSL or a general ill test in AFNI. So we want left more than right. So we know that left and right are the first two entries. So we can ignore the left arm and right arm. So we put zeros for those. And then left is a 1 and right is a -1. Okay, so that will give us left greater than right. All right. Any questions on that? Okay. For number 2, we care about did it activate in either the left or the right foot. So because there's an or there, we know we want an F statistic. Okay. And so we're going to write it down like this. And so in one case we want the left foot. Okay, and in the other case we want the right foot. So that's all we would need for that that contrast matrix. All right. So I think that's probably a good place to end for today. Let me just, okay, well, let me do 2 more slides, okay, just so we can end it with the F statistic. So the F statistic, just to summarize, is slightly different from the t-stat in the sense that you need to supply it both 2 degrees of freedom. One is determined by the number of rows in your contrast matrix, and the other is your typical degrees of freedom that we talked about before, which is the same degree of freedom you had for the t-statistic, which is that number of rows minus number of columns. So for example, in this case, if this was our contrast matrix, then R would just be equal to 2 because it has 2 rows. Okay, and then n minus k, this would correspond to, let's say we had 2 columns, 100 time points, and 2 columns. Okay, so that's the degrees of freedom that will be computed for your F-stat. And so this is the last thing I want to go over. So in general, if I only have 1 row for my contrast matrix, then the F statistic is just the square of the T statistic. Okay, so that's good. So for example, let's look at this. If I want a critical value for 5% for F at with degrees of freedom of 100 along this column of 1, then that value is 3.94. Okay, and if I go back to the previous table, that T of 100 is 1.984, and that squared is just equal to 3.94. Okay, so when there's just one sort of contrast, T and the F are basically the same. But when you're wanting to look at multiple contrasts all at the same time, that is when the F statistic is going to be different. Okay, so any questions before we end? Okay, so we'll pick up again on Wednesday, and then we'll sort of complete our single subject analysis on Wednesday. Right?
Tom,
Yes?
R and K are always the same, right?
Excuse me?
R and K are always the same.
Sorry, so R is going to be, R and K can be different when we actually have contacts.
Oh.
Yeah, so we'll talk about that some more
Okay.
On Wednesday.
So R is
R is determined by your contrast matrix. So in general, it's going to be
your contrast matrix, but not your matrix that includes
the design. Yeah. So right, exactly. So for example, let's say your regressors R might be 4, but you might have your total number of regressors might be 10.
Yeah.
So that in that case, K would be equal to 10.
Okay.
Yeah.
Thanks.
Sure.
Thank you.
Yep.